A spacecraft launched in 1977 to photograph two planets is now detecting a sound in a place where no instrument has ever listened before. The question is what Voyager 1 is actually hearing in the space between the stars, and whether this signal proves the void is not silent at all. For 46 years, the standard story was simple. Voyager 1 would drift into empty darkness after its planetary tour ended, carrying a golden record as a relic and sending back nothing but confirmation that interstellar space is a cold, featureless vacuum. Then, in 2012, after crossing the boundary where the sun's wind stops pushing outward, the probe began transmitting data that forced scientists to rewrite that picture entirely. What it detected was not silence. It was a faint, steady hum, resonating through the plasma itself, described as a narrow-band vibration no other human-made instrument had ever recorded. This is not metaphor. The hum is real, measurable, and continuous. It sits at a frequency of about 3 kilohertz, low enough to resemble the sound of gentle rain falling on a distant tin roof when scientists convert the electromagnetic oscillations into audio frequencies the human ear can process. Before the end of this video, you will understand exactly what mechanism creates this interstellar tone, why it was impossible to hear inside the solar system, what the rising pitch of the hum reveals about the medium Voyager is moving through, and why the signal matters more now than it did when the mission began. Because the probe's power is fading, and the window to hear anything at all is closing. The old model predicted that interstellar space would be mostly silent except during violent solar storms. When the sun releases a burst of charged particles, those waves ripple outward and cause the surrounding plasma to vibrate briefly before fading back to quiet. Scientists use those storm-driven bursts to measure plasma density for decades, waiting for eruptions to generate enough signal to detect. Between storms, they expected near silence. Voyager 1 has now spent over a decade beyond the solar system's edge, and the data it sends back does not match that prediction. Instead of silence, punctuated by bursts, the probe detects a constant low hum that never stops, even when the sun is calm. The tone does not spike and fade. It persists week after week, month after month, year after year. That steadiness is the first contradiction. The mechanism behind the hum begins with plasma itself. Interstellar space is not empty. It is filled with ionized gas, a thin soup of free electrons and ions drifting in the void. When electrons in plasma are disturbed, they do not simply scatter. They oscillate together at a natural frequency determined by their density, creating waves of electromagnetic vibration that ripple through the medium like sound waves ripple through air. Voyager's plasma wave instrument detects these oscillations as electrical signals. The instrument was never designed to be the probe's primary plasma sensor. That role belonged to a different detector, which failed in 1980. Engineers repurposed the wave instrument to listen instead of measure directly, and in doing so, they discovered something the original sensor would have missed. The hum is not produced by solar activity. It is the natural resonance of the interstellar medium itself, a baseline vibration that exists because the plasma is always there, always dense enough to sustain oscillation, and always outside the sun's overwhelming radio noise. Inside the solar system, this faint signal was drowned out. The sun generates a constant storm of electromagnetic interference that masks subtle vibrations in the surrounding plasma. Voyager had to travel more than 18 billion kilometers, beyond the point where the solar wind stops and the interstellar medium begins, before the background noise dropped low enough for the hum to become audible. The crossing happened in 2012, and the tone appeared shortly after. That timing is the second contradiction. If the hum were an artifact of the sun's influence, it should have faded as Voyager moved away. Instead, it grew clearer. The hum's frequency reveals something even more precise. Plasma oscillation frequency depends on electron density. A higher pitch means more electrons per cubic meter. A lower pitch means fewer. Over the years since 2012, scientists have tracked small but measurable increases in the hum's pitch. The tone is rising. That upward drift proves Voyager is moving into regions of interstellar space where the plasma is getting denser, not thinner. The old model assumed interstellar density would remain roughly constant in the local neighborhood. The hum shows that assumption was wrong. The medium has structure. It has gradients. It has regions where gas clouds thicken and thin, and Voyager is now mapping those variations in real time by listening to the tone. The third contradiction is how the hum was discovered at all. Before Voyager detected the steady signal, plasma measurements in deep space depended entirely on transient events. Scientists had to wait for the sun to erupt, then measure the resulting plasma wave as it passed the probe. Those bursts provided snapshots, not continuous monitoring. The hum changed that. For the first time, researchers have a constant baseline signal that allows them to track plasma conditions between solar storms, revealing fluctuations and trends that were invisible before. The steady tone is not just a curiosity. It is a new measurement tool. And it works only because Voyager is far enough from the sun for the interstellar medium's natural resonance to dominate the signal. No other human-made object has reached that distance. No other instrument is listening. The data Voyager sends back arrives on Earth 22 hours after it is recorded. The probe is so far away that radio signals, traveling at the speed of light, take more than 22 hours to cross the void. Every data point is a message from yesterday. The transmission itself is fragile. Voyager's downlink speed is 160 bits per second, thousands of times slower than an old dial-up modem. To detect the signal at all, engineers rely on 70-meter radio dishes, the largest antennas in NASA's deep space network, pointed at a single spot in the sky for hours at a time. The probe's power comes from plutonium decay, and the output drops by about 4 watts every year. To extend the mission, NASA has already shut down heaters, switched off backup systems, and turned off several scientific instruments. The hardware still running was designed in the 1970s. The onboard computers have less memory than a modern car key fob. Data is stored on a digital tape recorder built for 8-track technology. The software was written in assembly code on paper punch cards. Engineers troubleshooting the spacecraft today must consult 45-year-old paper manuals, because much of the original documentation exists only in filing cabinets. The fact that the probe still works at all is a contradiction in itself. The fourth contradiction is temperature. To save power, NASA turned off Voyager's internal heaters years ago. The electronics now operate in temperatures approaching absolute zero, far below the design specifications from the 1970s. Components that were never tested for extreme cold continue to function. Thrusters that were built to fire for 5 years are still firing after 46. The craft's orientation system, designed to keep the antenna pointed at Earth during a short planetary tour, is still holding alignment across 24 billion kilometers of drift. The resilience is not a design feature. It is an accident of over-engineering and luck. And it is the only reason the interstellar hum was ever detected. If any one of a dozen critical components had failed on schedule, the mission would have ended in the 1980s, and the steady tone would still be unknown. The hum's discovery also exposes a gap in earlier models of the heliosphere, the bubble of solar influence that surrounds our star. Scientists once believed the boundary between solar wind and interstellar plasma would be sharp and stable. Voyager's data showed it is neither. The edge ripples. It moves inward and outward, depending on solar activity. The density of the interstellar medium presses against it, and the hum's rising pitch suggests that pressure is not uniform. Voyager is drifting into a region where the local interstellar cloud is denser than models predicted, and the boundary between solar and interstellar space may be closer to the Sun in some directions than in others. That asymmetry was not expected. The fifth contradiction is what happens next. Voyager 1 is still transmitting. The hum is still audible. But the power budget is dropping, and by the early to mid-2030s, the probe will no longer have enough electricity to run its radio transmitter. After that, the craft will continue moving at 61,000 kilometers per hour, deeper into interstellar space. But it will be silent. The data stream will stop. The hum will still be there, vibrating through the plasma around the probe. But no instrument will hear it, and no signal will return to Earth. Voyager will become a metal tomb, carrying its golden record, drifting through the galaxy for millions of years, with no way to report what it encounters. The contradiction is not that the mission will end. The contradiction is that the most important measurements are happening now, in the final decade of transmission, and there is no backup. No other probe is close. No replacement mission is funded. Voyager 1 is the only ear humanity has ever placed in interstellar space, and when it goes silent, that ear closes. So what is Voyager 1 actually hearing between the stars? The answer is clear. It is hearing the natural resonance of ionized gas in the interstellar medium, a steady electromagnetic hum generated by electron oscillations in plasma that exists independent of solar activity. The tone is real, measurable, and continuous. It proves the void is not silent. It proves the interstellar medium has structure, density gradients, and dynamic behavior that earlier models missed. It proves the boundary of the solar system is more complex than a simple edge. And it proves that the region Voyager is moving through now is denser than scientists expected when the probe crossed into interstellar space in 2012. The old explanation that interstellar plasma could only be measured during solar storms is eliminated. The hum exists in calm conditions. The old assumption that interstellar density would be uniform is eliminated. The rising pitch proves otherwise. What remains unexplained is how far the density will continue to rise, whether Voyager will pass through the edge of a local gas cloud, and what other structures exist farther out that no instrument will ever reach. The hum does not tell us what lies beyond Voyager's path. It only tells us what is here, now, in this thin slice of space, 24 billion kilometers from home. The verdict changes how we read the data. Every new transmission is not just a status update. It is a measurement of a place no human will visit, taken by an instrument that will never be replaced, during a window that is closing. The hum is not background noise. It is the voice of the medium itself, and Voyager is translating it into data we can analyze before the signal fades. When the probe goes silent in the 2030s, the interstellar medium will still be humming. We just will not be able to hear it anymore. If you want to understand what else we are learning before the transmission ends, stay with the channel.